We've seen in previous videos that divergence is the mathematical operator which tells us how much of something is flowing out. We have the divergence theorem, and in this particular video, we are going to derive the divergence theorem. So, what we have is the area integral of J, which is in this case a current density, but could be any vector field dA, is equal to the integral of the divergence of J over some volume, over the same volume. So that's going to be equivalent, and that's what we're going to derive. Charge is conserved. Charge is conserved locally, not just globally. So what that means is that if we have some box, some region of space that has a certain amount of charge in it, that amount of charge can't change unless charge flows in or out. So the Q that we start with minus the Q that flows out plus the Q that flows in winds up being equal to the charge that we end with. This flowing charge is known as current. I is the charge derivative, or the time derivative of charge. Moreover, we can also define a quantity called J. J is the surface area current, and one way to think of J is that I is the integral of J dotted with some area. In the situation where J is entirely constant, which happens when dA is very small, we can pull this out, and that just makes the current equal to the current density times that area. We have a box. This box is an arbitrary region of space. The box with an arbitrary region of space has current flowing in and current flowing out. Our charge inside of the box is changing. Now, specifically, the size of the box is dx, dy, dz, and the total current, we'll just focus for a second on the x direction, is the current flowing in one side minus the current flowing out the back. So we could say J on the front minus J on the back gives that total current density if we multiply by that area. So I, in the x direction, is going to be J evaluated on that front surface dot dA plus the same thing evaluated on the back. But there aren't just two. So if we only wanted the Ix, we could just take those two sides. But if we wanted to have our full current, instead of just having Ix, we could have all of I, and that would become the front plus the back plus what we'll go ahead and call the left plus, of course, the right plus the front J dot dA and the back. So this is our total current for our region of space. That total current for our region of space, well, if we evaluate it at the front and at the back, we're going to have slightly different J, and we're going to have slightly different J here and here and here and here. And what we can say is that this right here is going to be J of x plus delta x, yz, which I'll suppress. And then this is going to be the integral of dy, dz, dy, not dd, dz, dy, dz, and of course there's an x hat here, and this would be the x hat here, so this just becomes the x component. So this is the integral on the front. Now when we do the back, we're going to wind up having J, now evaluated at x as opposed to x plus delta x because we're on the other side, dy, dz, and we have an x hat. Well, it's not actually an x hat anymore. What we now have is a minus x hat, because the surface normal vector is on the other side. So we've still got our x hat here. Let's make that a little more clear. Our x hat here, this x hat and this x hat, when we dot those together, will wind up giving us a minus sign out here. So now we have this integral, j of x plus delta x dy dz, minus the integral of j dy dz. And because we're integrating the same way, we can now combine our integrands to give us the integral of j of x plus delta x, delta x minus j of x dy dz. Well, j of x plus delta x minus j of x should remind us of something, especially if we were to take our volume and make it smaller and smaller and smaller. The process of taking our volume and making it smaller and smaller and smaller is gonna, j of x plus delta x, that's a derivative, especially if we wind up dividing this by delta x and putting a delta x over here as well. So delta x on the bottom, delta x on the top. So this becomes the integral of the partial derivative of the x component of j, because that's all we've been dealing with. This is the x component of j all the way through. So the partial derivative of the x component of j with respect to x, dy, dz, and we picked up a dx. Well, that's pretty neat, because we've just gone from our area integral into a volume integral, and we've picked up our partial derivative of j, the x component of j with respect to x. If we do the same thing, not just on the front and the back, but on the left and right, I missed this a while ago, this should be top and bottom. So, front and back, left and right, and the top and the bottom. The left and right, of course, would give us our partial derivative of the y component with respect to y, dy dz dx, plus this would give us the z component, and we can combine all of this. The x component of j, taking the x component of j's derivative with respect to x, plus the derivative with respect to y of the y component of j, plus the derivative with respect to z of the z component of j, gives us the divergence of j dx, dy, dz, which we can write more compactly as d tau. The nice thing about putting it as d tau is that what we have is now something that's independent of the Cartesian coordinate system. So we showed that all of this was equal to the divergence of j d tau. But there's something else this is equal to as well. Because we have the front, the back, the left, the right, the top, and the bottom of our cube, we have the only 6 faces of the cube, and each of these area integrals combine into one big integral that is a closed surface. We have counted for all of the dA, and the volume that we have our divergence coming from is entirely enclosed inside of this area. We can combine our integrand, because it's the same throughout, and we wind up having dA. What this video showed is that when we have a certain amount of charge, the charge can flow out, the charge can flow in, but the charge must be conserved. We used that to talk about the current density and the divergence of the current density, which tells how much charge is flowing out. That integrated over an entire volume, whatever our enclosed space is, will wind up being equal to whatever the current density is on every bit of that surface added together to make one area integral.